Welcome to this Spirent presentation on MPEG compression. This presentation will give you an overview on the basics of how MPEG compression works.
How does MPEG compression work? Well, there are many different tricks within MPEG that can be used to compress the video, but one of the key components at the heart of MPEG 1, MPEG 2, MPEG 4, many other different types of non-standard codecs, as well as JPEG, which is used for the compression of still photographs, is a discrete cosine transform, or DCT for short. How does this work exactly? Well, without getting too involved in the intricacies of high-level mathematics, let's take a brief overview. First of all, we need to look at a block of data within the picture, which is typically 8 pixels by 8 pixels. We look at the values for each one of those pixels, which is going to be used to represent the color and intensity of that portion of the picture. And what we're going to do is apply the discrete cosine transform, which is going to basically convert this picture from what is known as a spatial domain into a frequency domain. Here is an example of the discrete cosine transform formula. But really, this isn't a math lesson today, so let's skip to the next slide, which will use a graphical representation to try and explain exactly what is going on with the DCT. Let's take a look at how the discrete cosine transform works with these three simple diagrams. On the left, we've got a square wave, which has basically been sampled by 5 different frequencies shown on the right. Underneath, you can see the representation of that square wave when we add the frequencies together. That is, wherever the frequencies intersect, we add the values together and we reproduce an approximation of the square wave. By adding more information to the graph, we can actually sharpen up the square wave. To do that, we would have to add more and more frequencies. What I want to show you here is that basically the human eye is more susceptible to the lower frequencies within the video spectrum. If you look at a TV picture and notice that it's a little bit softer, it's softer because most probably too many of the high frequency components within the picture have been taken out. The more high frequencies within the picture, typically the sharper the picture is going to look. Within MPEG, one of the tricks that's applied to reduce the amount of information is to strip out some of these high frequency components. Now, let's take a look at the square wave if we reduce the amount of information. You can see below we still have an approximation of the square wave, but it's got a little bit more softer or raggedy. If we take out more information, the picture becomes effectively softer and softer. However, if we take out the low frequency component, we're going to lose basically all coherence in the picture. Like so. So although we've got all the high frequency components, because I've removed the low frequency, we've really lost the square wave completely. And this is very much analogous to what's going on within the MPEG algorithm. It's by taking out the high frequency components within the picture that we can apply additional compression. However, there is a point: if you take out too many high frequencies, the picture will become noticeably softer. Typically, this is easily spotted if you see some text on the screen and you see a form of ringing around the edges of the text. This means that most probably the picture has been overcompressed. Let's take a look at how the DCT, or the discrete cosine transform, is used to compress the video signal. Here we can see the results of running the DCT on our 8 by 8 grid within the picture, the 8 pixels by 8 pixels. These are the results, but at this point no compression has really been applied to the signal, so we could get back to the original picture. What we're going to do now is apply the quantization table to reduce the number of high frequencies within the picture, and also, by doing so, reduce the amount of information. The first step is to take the first number in the top left-hand corner of the discrete cosine transform results and divide it by the top left-hand number within the quantization table. So here we get the result of 27. We continue to work our way through the table, dividing all the numbers in turn by the quantization table. you can see that the quantization table increases in value as we move down towards the lower right-hand corner of the table. This basically results in reducing the number of high-frequency components within the picture, and as you can see, in many cases the numbers are simply reduced to 0. By doing a run-length compression now to the results, zigzagging through the table, we can reduce the number of zeros further. Finally, we apply Hoffman encoding, which is a form of symbol encoding, and we greatly reduce the amount of information transmitted in the signal. Now, of course, we do have a lossy picture. That is, we've compressed the picture, but we can never quite get back to its original form. However, hopefully, by reducing the amount of high-frequency components within the picture, we can fool the human eye into believing it's still a high-quality signal. If too much compression is applied, then of course the picture will become softer or blurrier. This will be a result of applying too aggressively the quantization table. Other types of compression are also available to the MPEG codecs. One is psychovisual video compression. The human eye is only susceptible to about 1,024 different shades, although modern cameras may be capable of recording literally millions of different shades. So if our camera is aiming up at a blue sky and can actually record millions of different shades, there's little point in transmitting this information when at the end of the day the human observer is only going to be able to discern 1,024 different shades. So by reducing the amount of information in the color component of the signal, we're greatly again able to reduce the amount of information transmitted. How is MPEG transmitted? Well, MPEG is broken up into groups of pictures. A group of pictures consists of I frames, B frames, and P frames. Initially, when a scene is filmed, it's constructed using an I frame. An I frame basically consists of the entire picture. The codec then waits. It may count, for example, 1, 2, 3, 4 frames into the future where it takes another snapshot. This snapshot is going to be regarded as a P frame. A P frame only contains the information which is different from the point in time where the I frame was originally taken. So a P frame may only contain approximately 40 or 50% of the information that the I frame originally contained. The B frames are basically predictions of how objects have moved across the scene. A B frame, for example, will relate back to the original I frame and also look at the P frame to see how objects moved across what is known as a macro block, a 16 pixel by 16 pixel array. The B frames contain all the information on how to render the objects which moved across the macro block and their direction or vectors. I frames, P frames and B frames are of course now recorded out of sequence. We first of all generate the I frame, then we generate the P frame, and then based on the objects and how they've moved, we construct the B frames. But of course all these frames are numbered, so when the receiving system receives a video stream, they're put back into the correct sequence. So although we transmitted I, P, B, 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 P, it'll be reconstructed at the far end into the correct sequence, which will be I, B, 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 P. So how does this work? Well, if we put it all together, we can now move an object across a macro block which is 16 pixels by 16 pixels. So the B frame contains all the information on how specific objects moved across this relatively small portion of the screen. That object is then applied to the background, which is derived from the P frames and I frames, and now we have the appearance of motion as that particular object moves across the scene.
Thank you very much for watching this presentation. If you'd like more information on Spirent equipment and products, please visit our website at www.spirent.com. And while you're there, don't forget to check the website to see if there's going to be a live seminar near you coming soon. For a copy of this presentation, you can visit my wiki at allentestwiki.pbwiki.com. You can download other presentations from the wiki as well, plus some other useful tools. If you'd like to look at other videos on YouTube, please search on Alan Talks Tech. Once again, thank you for viewing this presentation.